So welcome back to part 2 of the video tutorial for the 2008 mechanics paper. So this is question 2. Tahi and Rua are at the playground. Tahi is sitting on the merry-go-round that is spinning clockwise. He is 3 meters from the center and has a speed of 1.5 meters per second. Draw labeled arrows on the diagram to show the direction of Tahi's velocity and acceleration. So, with circular motion, in order to actually be moving in a circle, there has to be some kind of force or something accelerating you towards the center of the circle. So the acceleration is going to be like this. And the velocity has always got to be at a right angle to the acceleration, because essentially what's happening is he's trying to move in a straight line, but it's being curved in by the acceleration here, and it doesn't just work. Like it ends up being another vector between them because it's acceleration, it's not another velocity vector. But that's how it works with circles. It's important that you understand this isn't the velocity coming in here, because obviously that's his movement, that's not actually his velocity or anything. So state the name of this acceleration. This is centripetal acceleration. Calculate the size of his acceleration. Well, this is the regular acceleration formula, but we're looking for the acceleration formula for centripetal acceleration, which is this one here. So AC is equal to v squared over r. And both of these are given to us here. We have the radius. This isn't the radius of the circle, but it's the radius of how far he's sitting from the center, so that is the radius that we need to use. And the speed is obviously 1.5 meters per second. So this is equal to 1.5 squared over 3, which is 2.25 over 3, I think. Yep. So that's 0.75, which is meters per second, or ms negative 2. State the direction of the horizontal force acting on Tahi, and clearly explain why there must be a horizontal force acting on him. Well, if we go back to this here, we can see that he has to be accelerated towards the center of the circle in order for there to be circular motion, because otherwise he's just going to move in a straight line. And if there's acceleration towards the center, that means there has to be a force directed towards the center, because otherwise he's just going to move in a straight line. The only reason he's moving is because there is a force there. If there wasn't a force, then yeah, it wouldn't happen. So state the direction of the horizontal force acting on him. Horizontal force is directed towards the center. This is English, not American spelling. Not that my spelling's that good anyway. Of the merry-go-round. Oops. A force has to be present. Has to be pulling, I suppose would be the right word. Acting is more precise, I guess. Tahi towards the center, for there to be circular motion. Otherwise, he would just be traveling in a straight line. Okay. Rua pushes the merry-go-round so that its period is halved. Explain exactly what this does to the size of the horizontal force acting on Tahi. Right, so essentially she's pushing it around, and then the velocity is going to decrease if the period is halved. Then the velocity isn't going to decrease. Sorry, the period is going to be halved, which means that the velocity is going to double, because I think there's a formula sheet here. Yep. So v is equal to d over t. So if t goes down, then that means velocity is going to go up by the same amount if distance doesn't change. And while we're here, so that means that velocity is going to double effectively if the time period is exactly halving like it says. So if the velocity doubles, then where's this is centripetal force here, Fc. So we can see here that if the velocity is increasing, then that's going to increase the centripetal force. But because, I think I kind of wrote over it, but this isn't just velocity, it's velocity squared. So if the velocity doubles, then that's going to effectively multiply it by 2. And that means that the force is actually going to be quadrupled, not doubled, because it's velocity squared, not just regular velocity by itself. So I think that's at the right place. Okay, so if the period is halved, Tahi's velocity doubles. When his velocity doubles, the forces acting on him quadruple. Quadruple? I'm not sure if that's right. That doesn't look right, but you know what I mean. Quadruple is shown by, this is shown by oops. Radius, I think. Yep. You probably don't need to talk about. Well, it helps if you talk about this because it explains it more. And the main thing is just this bit here. If you said if you say that the force just increases, then that's not wrong, but it's not exact because it tells us exactly that the period is halved. So it's much more precise to say it quadruples, and that shows that you understand the relationship between the force and velocity. It helps if you can spell quadruple as well. Okay, Tahi then climbs to the top of. Oops, there we go. Tahi then climbs to the top of the slide. The slide is 4 meters high. He slides down. Assume all the gravitational potential energy is converted into kinetic energy. Okay, so there's no energy turned into heat or sound. At the bottom, he collides with Rua, who is initially stationary. Tahi's mass is 55 kilograms, and Rua's mass is 65 kilograms. Okay. And the collision is inelastic. State what this means. So, in an inelastic collision, I believe that's where... Is that where the velocity stays the same, or the momentum stays the same? I'll come back to that, I'm not entirely sure. Calculate their combined speed if they stick together after the collision. Okay, so combined speed. So we need to work out the momentum. And this, we've got P equals mv, but we're going to have to use the extended form of this, which isn't on the formula sheet. So P is equal to mv, but how it works when you have two different, obviously they go into collide and then continue. You have the extended equation, which is m1u1 plus m2u2 is equal to m2u2 plus, oops, that's, never mind, is equal to m1 v1 plus m2 v2. And the u here, they're still velocity, but it's just to get, so you don't get confused, because the masses generally aren't going to change in a collision, but the velocities will. So m1 and u1 are going to be Tahi, and m2 and u2 are going to be Roa. So we have Tahi's, we have both of their masses here. So we've got 55 for Tahi, 55 times, what's his speed? Okay, we're going to have to work out his speed, and if we look at the information here, we have his height, and we have his mass. So what we can do is work out the potential energy, and it says here, the potential energy is converted into kinetic energy, and with kinetic energy we can work out what the velocity is. So we'll have to, I'll come back to this. So the distance, it's 4 meters high, 55 kilograms. So E potential is equal to, what is it? It's mgh. So 55 times 9.8 gravity times the height, which is 4, which is equal to 2,156. And this is also equal to his kinetic energy. So Ek is equal to half of mass times velocity squared, which is equal to half of 55 times velocity squared. And we can rearrange this so we get velocity squared is equal to Ek divided by, times 2 if we're dividing by fractions, over 55, and this is equal to 2,156. Over 55. Okay, so this is velocity squared is equal to 78.4. So velocity is equal to the square root of 78.4. And we could, I'll show you here, that the square root of 78.4 isn't a particularly nice number, but we can round that to 8.85. Generally I'd say it's better to just keep using this, because this is the exact amount, and this is, you don't really want to use this because this is rounded anyway. This isn't the exact number, it's what the calculator rounds to. So this is the velocity, and I've run out of room, so I'm going to write on the back of some paper. I'll try and continue it here, hopefully you don't get too confused. So if we go back to look at this, so we've got, I'll write it here again, m1 u1 plus m2 . Okay. And we know that this is equal to 55 times the square root of 78.4 plus 60, where's Brewer's mass? Yes, it's 65 kilograms. So this is equal to 65 kilograms times 0, and this is the same as their end velocity, and their end velocity, their final combined velocity, it is going to be combined. Their they're basically moving at the same velocity here after the collision, so we can actually change v1 and v2 to just v, so this is going to be equal to v times m1 plus m2, which is obviously equal to v times 55 plus 65. So if we work out this here, times 55, and obviously anything times 0 is going to be 0, so this is equal to 486.99 is equal to that, and so that's 110, is it? 120. Yep. So we can divide both sides now to find velocity. We can divide both sides by 55 plus 65, or from 120. So then we get 486.99 divided by 120 is equal to v. Which is equal to 4.05825, so that's 4.06 to 2SF. What was the actual question? Okay, so it was asking for their combined speed if they stick together after the collision, so that's what the answer is. I'll try and fit it in here. They don't give you a lot of space to work all of that out, really, but... Okay, is Tahi's momentum conserved as he moves down the slide? Okay, so momentum can be conserved if there are no external forces. But, as we see here, there's obviously the force of gravity, because he's elevated, and so the force of gravity is acting on him. That's an external force outside of the collision. And then there's also friction, because they're moving down the slide. So if, instead of Tahi going down the slide and pushing into Rua, if they were both floating anti-gravitational hovercrafts brushing into each other, then momentum would be conserved, but there are external forces here, so it's not going to be conserved. And the external forces, they're external because they're not part of the collision, basically. Acting on Tahi. Right. Okay. I'm going to pause the video here quickly because we've reached about 18-19 minutes, and I'll restart. Well, I won't restart. I'll continue on in a third video, so see you soon.